So let us now start with the behavior of real gases. Until now, we have studied all all the things like different gas laws, and then we studied the kinetic model of the gas. So all of those were for ideal gases, but in real situation, ideal gas doesn't exist, right? So there are real gases that exist, and so we need to study the behavior of real gases as well. So at particular temperature and pressure that we will study later, all real gases behave in the ideal gas behavior. So let us study the behavior of the real gases that are actually present. It has a deviation from the ideal gas behavior, right? Our theoretical model of gases corresponds to very well with the experimental observation. Okay, now that we saw in the kinetic theory, theoretical model of gases. Now difficulty arises when we try to test how far the relation PV equals to nRT reproduce actual pressure, volume, temperature relationship of the gases. So in actual, so there has to be some deviation from this when we talk in the real sense, because this equation was formed on the basis of ideal gases. Okay, so when you try to you know make this work in the real sense, in the actual pressure volume temperature relationship, then there has to be some deviation. To test this point, we plot PV versus P plot of gases, because at constant temperature PV will be constant, right? So this will be constant if PV at a constant temperature, PV equals to constant, right? So if we plot PV upon PV versus P, then what will happen? So PV versus P graph at all the pressure will be straight line parallel to the x-axis. Okay, that means PV equals to constant, right? So let me write. So taking this equation into consideration, PV equals to nRT. So at constant temperature, if you want to plot PV versus P, then how can you do that? So we know this equation, Y equals to mx plus C, right? Here, but we are saying here Y will be P. So here it will be, everything will be constant, right? And where is X? There is no X. So that means there is 0 P. Plus the constant here is nRT, right? So what do you think when you draw the plot for PV versus P, then what do you will get as slope? Slope will be 0, right? So that means slope 0 means it will be parallel to the y-axis, sorry, x-axis, that is the P. So the ideal gas behavior in general should, when you plot the graph between PV and P, it should be parallel to the x-axis. But in real sense, here there is given, it is given different that of different gases like hydrogen, helium, carbon monoxide, and methane is given, and you can easily see the deviation from the ideal gas behavior, how it is deviating. You can see by the graph, right? Now, it can be seen easily that at constant temperature, PV versus P plot for real gases is not straight line, but it should be straight line according to this equation. That means this equation will not be followed by the real gases. There has to be some deviation. So there is a significant deviation from the ideal behavior. Two types of curves are seen. There are two types of curve again here also. So these four are real gases. This is the ideal gas, it was present. So there are two types of curve. One type of curve is this type, and another type is the curve type. Okay, so let us now study what are these two different types of curves. Both are real gases, but then also the curves pattern is different. So two types of curves can be seen in the curves for dry hydrogen and helium. As the pressure increases, the value of PV also increases and it is linear. But in the second type of plot, it is seen that in case of carbon monoxide, methane, so in the initial values of pressure, in the lower pressure values, PV first decreases, but in higher pressure, PV there increases. So first there is a dip and then there is a rise. So the PV value decreases with the increase in the pressure initially and reaches to a minimum value which is a characteristic of a gas. So it is minimum value is different for different gases. So that is why it is said that this minimum value is the characteristic of the gas. After the PV value, after that PV value starts increasing with further increase in the pressure. Now the curve that then crosses the line for ideal gas, and after that shows positive deviation continuously. It is thus found that ideal gas do not follow real gas do not follow ideal gas equation perfectly in all the conditions. So when do you think that this gas will follow the ideal gas behavior? When the pressure is this and the pressure into volume will be this particular coordinate, and in methane will be at this particular coordinate, right? And yes, so deviation from ideal behavior also becomes apparent when pressure and versus volume is drawn. Now, when you draw pressure versus volume, then in case of ideal gas, we know it is just inversely proportional. That is 1/x graph is there. But for real gases, there is some deviation. Okay. So the pressure versus volume plot of the experiment data that of real gases, and that theoretically calculated from Boyle's law, that is the ideal gas, should coincide, but it is not coinciding. It can be seen from figure 5.9. So figure 5.9 shows this plot. It is apparent that at very high pressure, so when the pressure is very high, then in that case the measured volume is more than the actual than the calculated volume. So the measured volume of the real gas is generally more than that calculated from the Boyle's law, that was for ideal gas behavior. But at lower pressure, the calculated volumes approach each other. It is almost same. So when you talk about at lower pressure, then you can say that real gases starts behaving like an ideal gas. Here also it can be seen at very low pressure. You see that your real gas behaves like an ideal gas. Okay. So it is found that real gases do not follow Boyle's law, Charles' law, and Avogadro's law perfectly under all the conditions, right? So now two questions arises. Why do gases deviate from the ideal gas behavior? What is inside the gases? So we have considered two things. First, we have considered in the ideal gas that there is no intermolecular force of attraction in the ideal gas behavior, but there has to be some intermolecular force of attraction in the real sense. And the second question is that what are the conditions under which the gases deviate from ideality? Okay, we get the answer. So we get the answer of the first question if we look into postulates of kinetic theory once again. We find that two assumptions of the kinetic theory do not hold good. These are there is no force of attraction between the molecule of the gases, and the volume of the molecules of a gas is negligibly small in comparison to the space occupied by the gas. So these two assumptions were taken when we were studying kinetic theory of gases. So which was for the ideal gas situation, and it was holding correct for the other gas behavior as well. And it was explaining Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law correctly, right? And definitely the equation of state, which is made up of all these laws. Now, but these two assumptions doesn't hold good for the real gas. That is where these gases deviate from the ideal behavior. So these two assumptions that there is no force of attraction between the molecules of a gas, but there exists force of attraction between the molecule of gas, though small, and also the volume of the molecules of the gas is negligible in comparison to the space occupied by the gas. This is also not true in case of real gases. So if assumption A is correct, the gas will never liquefy, but in real sense, gas does liquefy, right? So, however, we know that gases do liquefy when cooled and compressed. Also, only compressed will not work. Cool, you need to cool it also in order to decrease the thermal energy, and compress in order to decrease this distance between the molecules, so that the if when van der Waals forces increases or the intermolecular forces in fluorescence increases. We have already studied this in this chapter previously. Also, liquids formed are very difficult to compress. This means that forces of repulsion are powerful enough and prevent squashing of the molecules in tiny volume. If assumption B was correct, the pressure versus volume graph of the experimental data, real gas, and that theoretically calculated from Boyle's law should coincide, but it is not coinciding. P and V, right? Pressure and volume relationship, if we see at constant temperature, then it should ideally, in either sense, for either gas behavior and the real gas should actually coincide with the ideal gas behavior, but it is not coinciding, right? So real gases show deviation from ideal gas laws because molecules interact with each other in real sense. At higher pressure, molecules of gases are very close to each other. Molecular interaction starts operating. At higher pressure, molecules do not strike the walls of the container with full impact because these are dragged back by other molecules due to molecular attractive forces. This affects the pressure exerted by the molecule on the walls of the container. Thus, the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. Okay, so you have this. Now, let me draw a container and show you guys. For example, this is a container and you have molecules here, here, here. So for example, this molecule, when it will collide with the walls of the gas, then only the pressure is exerted, right? Sorry. But in real sense, we know that exists force of attraction also. So this particular molecule will not allow this molecule to coincide. So it will attract it. It will try to attract it. Now there is another force acting in this direction. So the impact of its collision with the container will be decreased in the real sense, right? So this means that the pressure exerted by the gas, the pressure exerted by the ideal gas is more than the pressure exerted by the real gas. Because in real gases, forces of attraction does occur, and there is another force that is applied against the colliding force, and that is why, in real sense, the pressure of the real gases is lower than the pressure exerted by the real gas is lower than the pressure exerted by the ideal gas. Okay, and that is why, and by how much it is less. So this is the correction term, a n square upon v square. Okay, now, so the pressure of ideal gas is pressure of real gas plus this term. So this term is used to, in accordance with in order to get over this attractive force. This is the correction term that is introduced, a n square upon v square. Repulsive forces also become significant. Okay. Repulsive interactions are short-range interactions and are significant when the molecules are almost in contact. This is the situation at higher pressure. So the repulsive forces causes the molecule to behave as small but impenetrable spheres. The volume occupied by the molecule also becomes significant because instead of moving in a volume V, now these are restricted to the volume V minus NB, where NB is approximately the total volume occupied by the molecules themselves. Here, V is a constant. Having taken into account the correction for pressure and volume, we can rewrite the equation as this. Now, we know what was the equation. Ideal gas equation was PV equals to nRT. So we already know that this P can be written in the real gas behavior as this. Okay, we just saw because of the intermolecular force of attraction. And we have assumed that the volume of the gas molecules is negligible in comparison to the volume of the gas, but that is not true at higher pressure. So we need to minus, so we need to subtract the volume occupied by the gases, that is NB, where N is the mole. Okay, so this is the correction term, and V is also the volume of the gases. So this is the total volume minus NB. So this will be subtracted. So this is the volume of the space now. Okay, it is not V, it is V minus NB. You need to minus the volume occupied by the total gas molecules, and now that will be equal to nRT. So this equation here, so the PV equals to nRT, that was the ideal gas equation, can be rewritten as this, which is the real gas equation. Equation 5.31 is known as Van der Waals equation. In this equation, N is the number of moles of the gas. Okay, so this is the Van der Waals equation. And you must know how to derive it from the ideal gas. Okay, now constants A and B are called the Van der Waals constant and their value depends on the characteristic of the gas. So in the question, you will be provided with the value of A and B, where A is the measure of magnitude of the intermolecular attractive forces as we studied with the gas and is independent of temperature and pressure. And also at very low temperature, intermolecular forces becomes more significant because the thermal energy decreases, right? So as the molecule travels with low average speed, these can be captured by one another due to attractive forces. Real gas show ideal behavior when conditions of temperature and pressure are such that the intermolecular forces are practically negligible. Okay, so the real gases show ideal gas behavior when the pressure approaches zero. So when the pressure will be zero, then there is no pressure. So gases are far apart. That is why you can consider that the volume of the molecule of the gases is negligible in comparison to the volume of the gas. And also at uh, very like low temperature, in that case, very high temperature, intermolecular forces of attraction is also kind of zero. So the real pressure ideal behavior when the pressure approaches zero. Now the deviation from ideal gas behavior can be measured in terms of compressibility factor Z. So which is the ratio of the product of PV and nRT mathematically. So if Z is equals to 1, then PV equals to nRT. So that means Z equals to 1 for ideal gases. But Z is not equal to 1 for real gases. There is some compressibility factor in case of real gas, which is not 1. Now the graph of Z versus P. So when you draw Z versus P graph, then what do you expect? So in case of when you draw Z upon P graph, so that is PV upon nRT versus P graph. So that PV upon nRT is constant in case of ideal gas. So if you draw PV upon RT versus P graph, then it will be straight line for ideal gas. We just saw sometimes before, but it is not such for ideal gas. So that means Z is not 1 for in real senses. So for gases which deviate from ideality, value of Z also deviates from unity. At very low pressure, all the gases show ideal gas behavior. So at very low pressure, okay, here it is Z equals to 1 only, all the gases approaches 1, Z equals to 1. So at very low pressure, generally all the real gases behaves ideally. And at high pressure, all the gases have Z greater than 1. So these are more difficult to compress. At intermediate pressures, most gases have Z less than 1. Okay, so at intermediate pressures, many gases have Z less than 1. It's only some gases like hydrogen, helium has Z always greater than 1. But at higher pressure, all the gases has Z greater than 1. Okay, so means when you increase the pressure, the compressibility is also increasing. So when you're increasing the pressure, you're actually making the gas molecules come closer, and that is why its compressibility is increasing. Okay, because the attractive forces are increasing. Thus, gases show ideal behavior when the volume occupied is larger, so that the volume of the molecule can be neglected in comparison to it. In other words, the behavior of the gas becomes more ideal when the pressure is very low. Okay, so the pressure is very low, then all the gas molecules are scattered apart and there is no intermolecular forces and all the real gas will behave ideally, right? So at low pressure that happens. Up to what pressure the gas will follow ideal gas law? It depends upon the nature of the gas and its temperature, right? The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called the Boyle's temperature or the Boyle's point. That also we for now, until now, we were studying everything, like when the real gas will behave ideally in terms of pressure. Now let us talk about in terms of temperature also. So the temperature at which the real gas will behave ideally for a particular range of pressure, that temperature is known as the Boyle's temperature or the Boyle's point. So the Boyle's point of the gas depends upon its nature. Above their boiling point, the real gas shows positive deviation from ideality, and Z values are greater than 1. The forces of after a particular temperature, okay. So above that Boyle's point is a particular its temperature, right? So above the boils point, the real gas always shows the positive deviation from the ideality, that is Z is greater than 1. The forces of attraction between the molecules are very feeble, okay. And now below boils temperature, real gases first show decrease in Z value with increasing pressure, which reaches a minimum value, and on further increasing the pressure, the Z value increases continuously. Now above explanation show that at lower pressure and high temperature, gas show ideal behavior. You can also understand this point using the intermolecular forces and the thermal energy cells. Now, these conditions are different for different gases. So, okay. More insight is obtained in the significance of Z if you note the following derivation. So, Z equals to PV upon nRT. So, if Z is not equal to 1, then V is real, right? So, volume to real gases, if the gas shows ideal behavior, then V ideal is equals to nRT upon P. So, on putting the value of nRT upon P by V ideal, we can write it as like this: Z for real gas equals to the volume of real gas upon the volume of ideal gas. When that gas that behave ideally, so that volume we need to divide by the real volume. So from equation 5.34, we can see that compressibility factor is the ratio of the actual molar volume of a gas to the molar volume of it. So all of these are molar volume that we're talking about 1 mole. Unless and until in the question it is given about anything about the moles, we take it as 1. So what we saw, that the compressibility factor is the ratio between the molar volume of the real gases upon or to the molar volume of the actual gases. Okay. So in the following section, we will see that it is not possible to distinguish between gaseous state and liquid state, and that liquids may be considered as continuation of a gaseous phase into into the region of small volumes and very high molecular attraction. We will also see how we can use isotherms of gases for predicting the conditions for liquefaction of gases. And now we will be studying about liquefaction of gases in details. So until now, we were talking that how you can liquefy gas by compressing it and also by decreasing the temperature, one can liquefy the gas. So what are other factors and how it is done? What is the critical temperature? We will also get to know about the critical temperature and critical pressure. And all of these we are going to cover in the next lecture. For today's lecture, only until here we will study. So from the next chapter, we will study liquefaction of gases. Thank you.